The talk is going to be about how to operationalize or getting actionable insights from your machine learning algorithms or stream processing. So to set the scene, we're just going to talk a little bit about how the evolution of analytics and what data, what role data is playing in the we have, if you take any industry or any devices you use, everything is designed to do one thing: generate data, and enterprises collect data, analyze data, understand how to use or how to better use data to upsell or increase their market share or increase their competitive advantage in the market. There is hardly any device which is not doing that. And there is tons and tons of data with utilities, telecoms, governments. Every industry is looking at data. In the past few years, because of data, we are also seeing a lot of convergence in the industries. Banking and telecoms is one such area where telecom providers are now trying to get into the consumer finance sector. So Apple Card is one example, but then Google and Amazon, they've all started to enter that industry. We also have social media and retail, e-commerce and consumer finance. It's all converging in a way that wherever there is customer data or wherever there is data and there is an integration can be made with the finance sector to make the conversion, they are going for it. So there is a lot of industry convergence happening. To facilitate this, the payments sector is more and more aligning themselves to do real-time payments and also real-time fraud. Because this, too, if you can achieve real-time payments, it is a very easy way to make sense of these industry convergence. You can apply or you can offer tailor-made offerings to the customer or the consumer in a way that he can make a decision and action it, which is good for the consumer and for the industry. So, having said that, we have a lot of data which is the historic data from which you get insights, historic insights, but then at double the rate, new data is being created. And without analyzing new data, it doesn't give you the full value. If you just depend on historic insights, you may not hit the consumer in a way that you are going to get, or you are going to get the conversion you are looking for. So there is two aspects. You want access to historic data fast. You also want to process live data or near-time data in a way that you can combine the insights and make quick decisions. So it's slightly different from what we have been used to, because it used to be descriptive. You always used to run reports, and still a lot of industries depend on reports. On top of that, if something happens, then you look at diagnosing that by looking at data in a way that they knew what to look for. When it comes to analyzing large data, different types of data, variety of data, it is difficult to know what was the actual relationship between the data that actually caused an event. Because when you analyze data, it is the human bias which kicks in. And you would look at data in a way that you think you will find the answer. That methodology was very good when you didn't have fast access to data, because you knew what to look for, you had time in your hands. Then it's okay. You can do that, and then that's a trial and error method. You can go wrong, and it's an evolutionary process, and you will get it in few tries, or you will get a near enough answer in few tries. That is okay until now, or it's already too late, but it's in the current market, that is not okay. Because you have a lot of data that is coming in, which you need to analyze for short-term insights, and also you need to use that short-term insights to shape your strategic insight and strategic planning. That is very essential in any industry. Otherwise, the market share just goes down, or something is not right. By the time they find it, it's too late. A lot of industries have gone down, which have been very big. In a space of like 2-3 years, they are no more to be heard. And hence, since those events happened after the last crash, financial crash, there is a lot of emphasis on harvesting data, even though they don't know what to do with it, but it's assumed that they will come to a point when they can actually analyze the data, and there will be a need for it. So everybody is holding on to data. If you look at a city, or you just take a picture of a street, you will know almost anything you can lay your eyes on is driven by data. Even from Uber Eats, analyzing what people are eating in an area and ensuring that the right kind of food is prepared for an area, to the taxi companies ensuring that the taxis are available at the right time, to governments using the data for various purposes to ensure everybody is safe, utility companies planning how much of energy needs to be made available, or if there are any proactive care needed, if it's any of their infrastructure being stressed and it needs repair. But in all this, whatever insight you are getting, there is a time value for it. Any insight you get, the value is diminishing with time. If you don't action the insight quickly, the value you're going to get out of it is going to be less, especially when there are very large enterprises with a lot of infrastructure power to actually do it. If there is it's a new company, you have found a gap in the market, it remains a gap until you find it. Once you have found it and you have joined the market, suddenly you know that that's been taken away. That's been filled by enterprises with a lot more power on their hands in terms of computation. That's very That's very much the truth. So what are the, so we've talked about why descriptive and diagnostic analytics aren't good enough. We have looked at how algorithms are shaping the way analytics is done, especially now that it is easy to get enough CPU power and memory power without shelling that much money. Thanks to cloud computing, everybody have access to it. Now you can use algorithms to analyze data, and algorithms can tell you the hidden relationship between data points, which was not previously known. So it is the insight, the quality of the insights that have gone better. Now you need to action them. Previously, there were very less use of algorithms, even though the use of algorithms itself to analyze data, that has been there for decades. It was the computation power and the availability of computation power which kind of held it back. Now that is not the case. You have the algorithms, you have the insight, but then you need to use it. If you then go to a developer and then say, we need to code this in a particular way so that we take use of this insight, by the time the developer has coded it, the application has gone live, the insights have changed. So you need it more adaptable. It needs to evolve quite quickly. You need to have a way any insight can be injected into your application stream quite quickly, because it is always evolving. So with Hazelcast, we have an open source way of doing this. How to action your insights quickly and in a way that you can easily update it so that it's an evolutionary process. So you have your existing data, which you have in Hadoop or database, wherever. You have your live data. You could then use, let's say, an algorithm like decision tree or random forest to identify an insight. So you've identified an insight, you've trained a model with your historic data. The model is now ready. Now you need to use that against your live stream so that you can get insights based on that trained model. To do that, you need a streaming engine which is going to allow you to do that, to use the model and process events against it. Take the insights and then use that insight to drive the decisions. So if you have a grid which is holding the data, giving fast access to data, and creating a lot of aggregates and KPIs, you have a streaming engine which has got the latest trained algorithm based on which you can derive an insight against data in motion as the data is flowing through. Then you have a ecosystem or a platform where you can better understand historic data, and you can use that straight away. So this could be like governments could use it when people are filling the form. As and when the form is being filled, it's being analyzed, and then the system decides what more information needs to be given. It's not a static form. Nothing is static anymore. You're not filling, everybody fills the same form. If everybody fills the same form, it's not just right, because you will miss a lot of things. you have expensive infrastructure like drilling, where you want to ensure that you don't break things because it's very expensive to repair, or there is no repair, or you just lose a lot of time, money, and effort. Then you have IoT sensors sending in all of the data. You have previous data from previous drilling exercises. You compare the current with the old, and you decide what's the best term in terms of how much stress you can apply, what's the rate you can function the machine. This is now actively used. People do that now because they now know that it's a better thing to do, especially in manufacturing industry, like an assembly line. If something breaks, the manufacturing stops, there is cost involved. Before even it breaks, it's best to get the sensors, get all of the data, and ensure that whilst the manufacturing is going on, none of your machines are being stressed, or if there is a manual error in the way machines are being used or configured, it can be found out. Otherwise, if there are minor differences in configuration, it is very difficult to find out. So when I say why this is an evolutionary process, there needs to be a life cycle for it, because you can train an algorithm, you can deploy an algorithm, you can have the real-time events being processed against it, insights being taken, but then as time moves, the algorithm is becoming more and more inefficient, because the algorithm itself has induced a change in behavior which is now no longer used to train the model, because the model was trained 1 week ago. Algorithm is running for 1 week. It has induced a change because the environment around it is adapted to it. If it was, let's say, a payment processing, there is an algorithm to detect fraud. It's been running for 1 month. The industry or the people who wants to do fraud, they have now assessed it. They're going around it. They have changed their ways. You need to now capture that, retrain the model, and then you put it in. So it's like an evolutionary cycle, which is going to help in this case. So operationalizing actionable insights or from data, that is an evolutionary process. Any platform would need to account for retraining of the models with the current or the latest data, and it should also account for replacing the trained models in the engine in runtime. There's no point stopping everything. So that's the thing. So how is this achieved? So Hazelcast used to be a in-memory data grid company. So it used to have only one product. It didn't. All it did was an in-memory data grid, which was good at storing data, fast access to data, compute on the data, and it also provided messaging. That was it. Now, recently, it's been about 3-4 years now, but they have, we have Hazelcast Jet, which is a stream processing engine. It is very good for data ingestion. You can combine multiple data streams. You could do windowing, temporal sequencing of data. You can compute, distributed compute. So you can have event processing defined as behind the scenes, it defines it as a DAG algorithm and distributes it across the several nodes in the cluster. And when an event comes, the event is processed in a distributed fashion. And when it does it, when it's distributed, when I say distributed, it has to then, is it going to then send at every stage, whatever is computed, is it going to distribute it across all of the nodes? No, that will be very inefficient. So what it does is it uses the IMDG for holding the data. IMDG provides distributed concurrency, so it basically creates or holds the data, which is the output of a part of the computation in IMDG, and that could be just one data, or it could be a collection of data. And then it basically informs the next node in the cluster to do the computation on that collection. And that node can either do it by pulling the data to the node, or it can do it straight on the cluster. The benefit is you can optimize network, you can optimize the use of CPU, and you can optimize memory. If you made multiple copies of the result and published to all nodes, you will be wasting CPU and memory. So any in-memory, any stream processing, distributed stream processing engine which is not optimized for with a distributed data grid, there will be wastage of CPU and memory. If it is, so let's just say if an application, if a streaming engine is optimized for local caching only, that means it has to send the message. If you send the message, then it's going to be delayed. And when it comes to very high-speed processing, like if a bank is providing a payment clearing service, you will have retail payments, you have payments which comes through their third-party agents, then even a slight delay will add up. You will not meet your SLA. And especially in payments industry, if you have the number of algorithms you can run whilst processing a payment is dependent on how quickly you can access the data. If your data access is slow, then the algorithms will also take time to run. And if you run less number of algorithms, more chance for fraud. So how does the platform look like? So you have a streaming engine. There's nothing great in it. So just you define what computation you want to do it on the events, and it will perform that action. But then you need to give some historic insights. If you hold that in-memory data grid, it's good. And if the in-memory data grid can be accessed by all of the Jet nodes, then they don't need to share data other than putting it in the grid. The in-memory data grid can also hold these KPIs in downstream or data stores like databases or Hadoop. You can also have some logic in it to load data into the grid with and recalculate some of the KPIs. Any streaming engine should have connectors or adapters which can allow it to take data, consume data, and output data in different ways. Without that, it doesn't meet its purpose. So there is an adapter framework which allows you to get data from various endpoints. With this, you could do a lot of things other than, so you could do something like a smart routing application. You don't need algorithms for that, or for simple versions, unless you want algorithms to do the routing. So it's like in invoicing industry, when there is, for a very large enterprises, where there's a lot of invoices coming, normally it's algorithms who learn where the invoices needs to be posted, and then the routing service itself is a machine learning engine, which use machine learning to define where a particular document needs to be posted. But in a normal case, you wouldn't need any of that. You wouldn't need machine learning if you want to detect patterns across multiple streams. So you have a stream of data coming through. Maybe there's a football game going on, and you're basically analyzing the crowd because they have apps on their phone, and there is Bluetooth beacons everywhere in the stadium. So the application knows where each and every persons are or interested people are, and there is a particular set of gathering which they don't want to happen, and that's based on that is how crowd control is being operated. In that case, the engine would detect patterns. If A and B are in this place, then C and D cannot be in that place, simplistically. So those kind of patterns it can do. To do algorithms, once you have trained an algorithm, so you could use, so Jet could, you can embed TensorFlow or JPMML engine inside Jet. Jet in itself is a 35 MB jar file. It doesn't have any dependencies. It is a streaming engine with no dependencies. You can either embed your application in Jet, or you embed Jet in your application. It doesn't have any dependencies, so it's very easy to do so. You can easily run a machine learning engine or execution engine inside Jet. And you can make a call from Jet when analyzing the stream, as one of the computation points is to actually call the machine learning engine, which has already got the trained algorithm in it, to quickly execute against the incoming data and give us the score or the KPI. So it can be like a scoring engine. If you have that set up, then you need a way to train the model. So R is a very good way of doing it. You can actually connect R runtime and any Java runtime. So you could basically use application to basically send a message to R saying that it's time to train the model, and you could have a script in R to basically take the data, train it, and keep it ready. And then it's down to the application when to actually pull that model in. This way you have the setup complete. You now have a method of training, a method of holding historic data, you have a method of injecting trained model into the streaming engine, and the streaming engine just use this as it's an extra intelligence. It makes a call whilst processing the event and gets the score, combines that with various other inputs it can derive, or it could be even reading 2 or 3 streams at any given point of time. One of the streams calls the algorithm, or you just make a parameter list across these multiple streams and calls into it. Now, this becomes more interesting if the streaming engine also does windowing. And Jet does windowing, so you're basically temporarily sequencing an engine, but you need to be able to slice it on a tumbling window or a sliding window, such that if you want to analyze the last 5 minutes, last 10 minutes, or every 5 minutes from yesterday, you could do that. You can just take the data, replay everything. And that's also one good way, because when you create these algorithms, you would train them and you would test them. And when you test them, you need to make sure that you are getting positive results, because you compare that with what your predictive result or what the model told you. Is that similar or the same as identical to what actually happened on your historic data? You split normally the data into 80-20. 80 is used to train, 20 is used to test. Make sure that 20, the results coming out of the model is exactly the same as the 20% of the test data or 80% of the test data, because once it's trained, you need to get accurate results. So when you have that kind of facility, you can then use multiple iterations quite quickly to train the model. Because every industry, every enterprise have a data science team. The data science team would use advanced analytical systems to define the data, and they will test it, and then it's down to the IT to actually take it, process it, and then also give feedback, or give the data scientists enough freedom or enough for the application such that they can do this themselves. They have a UID space where they're just going to deploy against a set data, and they just keeping on. They're always training and identifying new models. So where are some of the other use cases? If you look at payment processing, this is a good use case for this because it's been widely used, and it's already most of the payment processing companies have trained algorithms, some of them very big, but they've been actively used. Because it is a very easy way now to get that historic insight actionable in production or against live data. So it's also used in infrastructure. Even in UK, you have companies who have got, for example, water supply, wastewater and drinking water. Infrastructure network is huge. The manpower to run the infrastructure is less. Sensors are there everywhere. They need to now identify which ones they should fix first. They cannot classify every issue as the same. They need to analyze the impact, and it's based on the impact, accessibility, and potential downtime that you send an engineer to fix it. Because if it cannot be fixed in good time, and there's going to be time wasted on it, when other jobs can be finished, or multiple other jobs can be finished in that time, they will just use that. And then maybe it's just a truck with drinking water posted and pumping water into the pipeline. Just an artificial way to keep everything running. So this is widely used. And online retail, I guess everybody knows that because everybody feels it. If you have Alexa and sometimes you would be having a conversation and related ads is going to come. I'm not saying Alexa is doing it, but sometimes it is possible that there are various devices. You don't have to actually go online. You just have to say or have a conversation, and you automatically get related ads on there. So the plan was to actually show a quick demo. I will actually talk through it because I think we are running out of time. So we just have a demo where we have some data from the telecoms industry about customers who have left the contract and who are renewed. So the model has trained on that data and can tell based on certain parameters like how much call time a customer is using, how much money they are spending, what time of the day they are calling, how many customer service calls they have had. Based on that, if you give all those parameters, the algorithm is going to tell what is the propensity for this customer to stay in contract or move away from contract. This means that they can have tailor-made offers when it comes to renew. Because if a customer is very happy, he's not going to move then perhaps there's no need to give him much offers. And if a customer is not happy, and he's likely that he will not be happy, then it's probably best to let him go. Or if the company deems that it is best to keep him because there are other people around him who's going to have the contract as well, or some other reason, then you can give him some offers. But in any case, the amount of money that is allocated to give offers to keep the market share, that can be adjusted. Spend a bit on the technology, and the cost of keeping the market share could go down. So it's a relevant use case. And here we have a jet engine, which has got the algorithm running using a JPML engine embedded. We have a Spring application, which is going to host a small web portal where you just put the phone number. Let's say, assume the call center has received a call from this guy, and they just check his number, and the system is going to say, okay, this guy is not happy, or he's very happy, and then you can decide, or the system can also, from a decision table, can tell what offers to give that customer, almost like a concierge service. So it could be any touch point. I mean, you can go online, and then you have some data which is held in the grid, which is used to train and or get details of the customer. So as a sequence, a request goes in, the customer details is fetched from the grid. You create the request, pass it on to, put it in a Kafka channel, and it just it's received by the Jet stream processing engine, and it will provide the results back in another channel, which is going to be read by the Spring application and displayed on the screen. Now, why this is not a request response system, it can also do a request response as well, but you can also have files with data, or you can stream a set of numbers to analyze all of them. What is their propensity? Because you can create, you basically segment and do segmentation on the demographic, and then say, okay, these are the segmentation the company wants to target. And you can then use the algorithm to analyze, okay, this segmentation which I'm going to target, what is the propensity for them to stay or leave? So I'll quickly show this. So we have a Jet. We have a Jet engine. We have with some data in IMDG, and we have the app. Oh, there's an exception, but that's because I was playing around, but it's all good. And what I will do is I'm going to put this on front and bring the presentation back. So, sorry. Thing with extending the screen is how can I type well. So let's just say 408, that's US phone numbers, and 340 hyphen 8323. So this is going to see, you can see there is a percentage. Yes, this person is likely to churn. I mean, he's going to leave the contract, and you can see the propensity. Maybe 80% he's going to leave, and 20% he's going to stay. That percentage is what is. This is not enough that you say, okay, he's going to leave or he's going to remain. What's the propensity? So that they can tailor what exactly. It's a bit more granularity to the data. So this demo believe it is in GitHub, but we are actually creating a bit more. We are basically updating this demo, so it'll be available in GitHub soon. Last but not the least, but I just need to just, whoop. Right. Okay. There you go. I need to see the cursor. Okay. So as a platform, it looks like this. So you have the grid underpinning the streaming engine. The streaming engine Jet on it can do things on its own as well. So it does give you ability to store some data, but we advise using in-memory data grid. And based on that, you can use you can create applications, and because the engine itself, it can do streaming and batching. I mean, it is not micro batching, so when it does streaming, it can do true streaming. You could use this for analytical processing, or machine learning, or you could use this as for IoT applications, fraud detection applications. That's the possibilities are immense with this type of approach, because a lot of industries are trying to ensure that the applications are more adaptable. It is very and written in a way that you have the ability to have these insights from machine learning as well. We have so with cloud and the container, there's a lot of container platforms, and so one of the options is to use OpenShift or PCF to create containers with a data layer, analytical layer, and your business layer, in a way that all the integrations are already pre-done, and you create a template, and then it's there available to easily program. So your time to market is now less, and you can have Kubernetes to manage the deployment, scaling, and controlling availability, etc. So that brings the talk to an end, and also conscious of the time. Any questions? We can go through them here or after the talk. Yes.
I was just wondering about this updating of machine learning algorithm and streaming engine.
Yeah.
I could understand the approach if the process would be real-time process. But if you really have a data science team which reviews if the algorithm made mistake later, isn't it better to train it then separately?
So that training would happen anyway, separately, because the data science team, their job is to keep training the data. But once you have committed something to live, you have put a trained model in there. Now, you are also monitoring what is the offset from what, let's say if it's predicting something, what is the offset of what the model has actually scored it or predicted, and what actually happened. If the offset goes beyond a threshold, then you need to change it as quickly as possible. So the platform needs to allow that. So as you said, there is that thing as well, but it can both coexist. Yep.
Is there any continuous loop you guys have in memory? Like if you put it in, as you rightly said, it might get changed, the ecosystem changes.
Yeah.
Because you introduce a change via the model, the
Yes.
change it does, right? It is a streaming model, so how do we do this historic memory retuning?
So it would be once you train a model and you export as PMML, it's basically a set of coefficients or a set of values based on which it's going to score. So and that will change when you retrain. So once you pull the model out, so effectively what would happen is that you basically have a job in the streaming engine. That job is to score. You need to update that job. So when you do like a rolling job update, system does a snapshot. The snapshot is a very small window. Snapshot, drop the job, create the new job with the new model, replay from the snapshot, and then you are live, and then it goes. But and in this setup, there's also it's quite important to actually monitor the value that is coming out and what's the offset between the thing.
My question is more, so we have found a new pattern, let's assume.
Yeah.
How do I rerun back to the history again to see if the pattern existed before? This is something we learn now.
Yeah.
But I've already been
To do that, you would need to be able to redo the stream. So if you are actually reading the stream and the stream is being stored, you can basically have another jet engine, another streaming engine, which is going to reconstruct the stream for you and then pull it back into the main stream.
Is there any persistent built in the framework for that? So we can just
No, that has to be, yes. Because the memory impact, that's huge. Because you cannot store an unbounded stream for an unbounded, that will require a lot of memory. So it's just for that. Thank you.